mic on? Oh, here we go.
Yeah, go ahead and say hello to the people.
All right. Hi, everyone. My name is Aaron. I am actually an internal product person for our laboratory information management system at PyBay. So I'm going to talk today, though, about some challenges in processing time series instrument data that we get from our scientific instruments. But I guess you're introducing me.
You're stealing his thunder.
Yeah, I can do that for him. I'll do that for you. Just compare.
Hold up a minute. Carry on.
Okay, this is Aaron Wiegel. I say that right?
Yes.
He's with PyBay. He's the product owner for LIMS, which is Laboratory Information Management Systems. The title of the topic is Using Pandas and PySpark to Address Challenges in Processing and Storing time series instrument data. He helps design software solutions for scientists, and he has a background in chemistry and switched to data science 6 years ago. He can help you switch careers too. Also, he has a microbrewer brewing at his home. So if you're interested in that.
Yeah, so you do some lab science at home still. Maybe not as clean as the lab, but.
You don't get a display over there, but I think you're okay.
Okay. All right, so my slideshow doesn't seem to be working, so we're going to do this the hacky way of just going down through the slides. So yeah, thanks for everyone to having me, PyBay for having me to talk today, and all you for coming and listening to my talk. So got a good introduction there. So kind of just an overview of everything, if it will show up. Oh, I think I know what's going on. Hold on a second. I think it dropped me from the Wi-Fi. Yep. Like, why isn't this loading? So give me a second here. Technical difficulties, please stand by. So while that's like sort of holding up, essentially what I'm going to talk about today is just give a brief overview of the company I work for, PyBay. Talk to you a little bit about laboratory information management systems, kind of what they are. I'm sure everyone knows the acronym LIMS off the top of their heads. And then kind of get into some meat there, talking about just a couple of different challenges that we faced, like sort of dealing with data coming from instruments. So let's get started. So PyBay, what is PyBay? Obviously, you're not a software company, you might guess from the name, but we actually are helping to build a solution for sustainable nitrogen in cereal crops, so corn, wheat, etc. So why is this important? Well, a lot of these crops are supported by synthetic fertilizer, which is produced by the Haber-Bosch process, and that's a really energy-intensive process that also uses natural gas as a feedstock. What we do is we actually create a microbe that actually replaces a lot of that synthetic fertilizer in just like grows in the roots of the plant and just provides ammonia to the root of the plant just by using sugar and from the plant, and then provides back ammonia as fertilizer. Why do we care about this? Well, synthetic fertilizer is, pollutes our waterways. It produces nitrous oxide, which is this third most potent greenhouse gas after carbon dioxide and methane. So what we do is we help solve this problem with this bacteria, but it also helps the farmers a lot too, because there's a lot of waste in synthetic fertilizer use. So they actually really like our products. It makes it more predictable of how much nitrogen there is. If it rains, it doesn't all water off because the bacteria just grows on the root. So win-win for everyone, win for the environment, win for farmers. So how do we go about saving the world then? Well, we need to make sure we track all of our research data as we're sort of developing products in our research product pipeline. We need to track all of that data, and that's what the sort of LIMS comes out. It's not just my arms or legs in this case, but LIMS stands for Laboratory Information Management System. So kind of what that is a system for tracking samples, the associated scientific workflows with those, and any kind of related data. So you can kind of think about it almost as like a warehouse tracking software, except instead of boxes, it's like tubes and things like that. So part of that's to manage inventory and sample stewardship, just so we know what we're actually measuring stuff is what we think it is. Sort of facilitating communication between different teams. So like in a larger organization, it's really important that sort of teams that sort of doing different functions in the lab are able to communicate what samples are and what they need done, and so on. The idea here is, of course, we want to save time and improve efficiency of research and development. We don't all this back and forth of what is this now? Oh, it's this. Can you go look at the spreadsheet over here? That kind of thing. And then finally, one of the key things is also want to sort of aggregate data from multiple experiments so we can generate insights about what's going on in our product pipeline, what are we sort of building and developing. So kind of here is just like sort of an overall schematic of like how data might flow in a lab. So it's kind of a mix of several different systems. We have like sort of a front end that a lot of the scientists would see, which would be like an electronic lab notebook software. But there's also all sorts of different. Microphone fell off. Different components to the system, including bioinformatics pipelines. It potentially might be incorporating external data or commercial data. And a lot of times people want to see this in like analytics software like Tableau or Jump if they're not necessarily a data scientist. So kind of that's a lot, but I'm going to kind of focus on this little part right here for today. So kind of the interaction between instruments, our electronic lab notebook and sample management software, and our data lake and data warehouse. So kind of like zoom in on that side right there. So we kind of rely on a lot of like software service products to do this. So like, for example, we use Benchling for our electronic lab notebook. We're using Databricks for our data lake / data warehouse. And with our instruments, there's everything, like anything you can imagine. So the way these sort of interact with each other is that when someone wants to go measure something on an instrument, they'll produce a sample list from our electronic lab notebook software. This could be sent automatically, or it could just be someone downloading a CSV onto a thumb drive. They get raw data back, which is often in very fun, different formats. And then as that data gets ingested into our electronic lab notebook, it gets copied into our data lake, data warehouse. I'll give you an idea of like the overall interaction of this whole system. So here, there's lots of challenges with instrument integration. A lot of times, the instrument companies, they're not software companies, they're hardware companies. So they have a lot of like proprietary or oddly formatted data. So like sometimes the concept of an API is a little foreign there. Some software companies are really good, or some instrument companies are really good about this, but oftentimes there's no API, there's no great way to interact with it in like a sort of automated way. And you could also run into issues depending on what you're dealing with, like data volume and size. So there's like a mix of like, perfect mix of like weird formats or like large data sets that kind of makes things a little fun to deal with. So I'm going to kind of go into maybe some of those challenges we face, kind of digging down deep into like a couple examples of sort of issues we've dealt with at my current company. So one thing we kind of deal with is like funky file formats. So a lot of data we get is time series data. So this will come from things like inline sensors in a fermenter. So like, for example, you get like measurements of pH or the amount of biomass or dissolved oxygen. Often to like ease like sort of the visualization of data for the scientists, the data is often formatted to line up with like wells on fixed well format microplates. So just because most of you probably aren't familiar with those, I kind of show a picture right here, where on the left there's sort of letters that designate the rows, and there's numbers at the top that represent like the different columns, and like people figure out which sample they're putting where by sort of using that coordinate system to figure out which samples go in each of those little tiny plastic wells. Because of this like sort of weird format that a lot of files come in, like the scientists are often need to write custom Python or R scripts. I promise that's the last time I'm going to mention R, to process and analyze the data. So like they often spend a lot of time like munging the data themselves, and they're not really experts on like using some of these things. They just kind of, it's just a chore that they do, and they just want to get something done. So here's an example of what one of those files potentially looks like. And you kind of see it's like very like multi-dimensional data with time and space here. So over on like the left here, we have the well, so that's the position I just talked about. And then you kind of see someone decided it was a great idea to make variable data the columns. So the time is actually the columns here, and each time you run one of these instruments, you get a different number of columns with different values in them. What we really want out of this, if we want to put this in a well-structured database where we can actually aggregate the data, is we want this measurement column over here, which says biomass gain, to actually be a column, not like a row value. So we gotta need to reformat this data in such a way that we can actually like reliably insert it into a database and not have to worry about weird cases, edge cases, and other fun things. So well, what package will we use that? Well, you could use pandas, right? You know, that's kind of the workhorse of data analysis and engineering in Python. So if we were really naive about pandas, we would just like do something maybe like this, where we divide the metadata that we have on the left there, and then we kind of go on the right, and we're like, oh, well, let's just like iterate through each one and sort of stack them over and over again. And one of the things that like, yeah, this code actually will work if you do this. Also, writing this code was one of the hardest things I've done recently, because it's not necessarily very native to pandas. And this will work and give you kind of this restacked data, but it's kind of ugly, it's kind of hard to follow. And honestly, because of the vectorized sort of implementation of pandas underneath the hood in NumPy, you probably don't want to be iterating through things in pandas. It's going to be slow, it's not going to work very well. And quite honestly, that code to me is just very ugly. So if you think about using pandas in a way that's sort of best practices native to how that actually works, when we could actually use a more native approach to pandas and use like sort of multi-indexing and stacking and unstacking. So what that kind of means is that we want to think about the indexes of our data as sort of the coordinate system that describes what each of the different values of the data we have are. So you'll see here when I load this Excel file into pandas, we actually specified index column of like 0 and 3. What that does is it takes that well and kind of format it funny, but the actual measurement value, and it makes them into row indices in pandas. You also see that we have a column index, which represents the time that we saw as those columns. Now that we have that, we can actually do a series of operations that may more intuitively make sense within the pandas API. So what we could do here is just do some little bit of data cleanup, and then we can just run df.stack. And that does exactly the same thing that for loop I showed you earlier does. All it does is it just takes that column there and it stacks it. And now what we have is actually just a vector that each of the coordinates represents the well, the measurement, and the time, and the value at that point. So taking that maybe ugly for loop, and now it's just one simple function that kind of makes sense what it's actually doing, right? It's just stacking it. We can do that again to kind of pivot the column names into what the format we wanted, where we could actually call unstack. So we take this vector we've created here, we unstack it, and now we have like a data frame that has the actual measurement columns as column names, and the well and the time is the row indexes. So we kind of maybe want a flat data frame, so what we can do is just reset the indexes, and we actually have this data now, once we've reset the indexes, in this nice format where it's like well, time, and then each of the measurements at that time. So putting that all together, we can load the data frame in again, specify what our indexes are, do some cleanup, stack the data to make that time axis into an X row index, and then unstack the measurements to get our column names. From here, there's maybe some cleanup we need to do of the data to make it a little more friendly, and then we actually have a pretty simple code snippet that we can then use on AWS Lambda to process this from events emitted by our ELN software and post a response back. It's kind of automating a lot of the interaction that the scientists normally would have, where they'd have to run scripts. Now they can just upload a file, and then the process data gets spit out. Here is sort of a simplified diagram of how this event ingestion might work. So we have our ELN software benchling. We could subscribe to an event from their event bus and sort of pipe that into our own AWS environment. And based on the event bridge rules that we set up to say, oh, it's this event happening from this sort of software interaction, we can use AWS Lambda to process that code or process that data with those few simple steps I showed you, and then post it right back into our ELN software as part of its database. So great, we automated something. We saved the scientists hours of time munging data. Now they just upload a file, click a button, and the data is in a nice format they can just use. All right, so great, we solved all the world's problems, right? Well, there's other sort of issues that we potentially have to deal with here, and that includes issues around data volume. So here's sort of another sort of issue we kind of dealt with. So in this case, we have still those same 96 well plates. We have these kind of an instrument where a lot of these are just stacked together, and there are measurements done over days that take each of these type of time series at each of these positions in this instrument. Here, the people who made this software were much nicer, and they actually put just a fixed number of columns for plate position as our column headers here. So this should be pretty easy to manipulate in pandas and put into a long format that we might want for our database. So we could just use pandas.melt. So here we can use the melt function here in pandas, and what this basically does is kind of same kind of unstacking, stacking I was showing before, but now instead of well being a column name, it's now a row value, and then we have the value at that well, at that time for this particular instrument. So that's pretty simple, right? Should be able to do the same thing we just did before without much trouble. Well, here is sort of the issue. After we melted this data, now we have 1.3 million rows of records. Went from 13,000 to 1.3 million. So what that sort of introduces as a problem is that so our ELN software has a row-oriented database. So as we're starting to add more records over time, this actually takes longer and longer with linear complexity. So I did some profiling of the software itself and just tried to insert 10 records, 100 records, and so on. And what we kind of find is that like as the sort of number of rows increases, it like sort of starts to like go very slowly. I don't know the reason why. I was speculatively, like I could say that potentially it's rebuilding an index every time you sort of insert records because you're limited by the software to 100 records per time with their API. And I didn't even really bother testing 1 million records because we already ran into a limitation at 100,000 records. And that kind of records is that since adding 1.2 million records is very slow with this software, the max timeout in an AWS Lambda, if we want to deploy the same kind of solution we did before, is 15 minutes. So we're already hitting a limitation of the software that we can't actually insert this many records. So then, when at the time we're like, oh, this should be a really easy feature to push out for the users. We'll just do this same thing we did this other thing. Well, then we're kind of like scrambling. It's like, oh no, like we didn't really scope this properly. What kind of alternatives can you do? Do you have to do parallel processing, work queues, like split this up and batch it and like sort of go all at once? Well, I could have done that, but one thing is to kind of realize if we kind of go back to this diagram from earlier, is that we're actually taking anything that got inserted into our electronic lab notebook software and we're copying it into the data lake. So, and like people don't want to look at this data one record at a time. One time point is like not that meaningful on its own. And like I said, the use case for some of this data is for analytics for a lab and data scientists. So maybe they're going to look at it in the data lake anyway. So we could actually come with a data pipeline here that actually solves some of this problem. So we could actually ingest the data as is. Don't do any file operations. Just take the data with the wells as the columns, just push it into the lab notebook software, and then just copy that over to the data lake. So here we'll kind of show a diagram where the user enters sample metadata about like what the samples are, what's in each well, and then they associate that metadata with a CSV that they upload with this raw data in it. The data, sample metadata and the time series data is just getting copied and staged into our data lake. And then we can do any transformations there to join that data to make it available as a data source for any kind of like analysis or data science pipelines downstream. So we could just ingest the data as is without processing it and just create views within our data lake that kind of show what that data looks like. So here I show an example of like how you can write a query in Spark SQL. And this is basically the equivalent of the melt function we showed earlier. It's just in SQL, so it's unpivot, and it's just a little bit different. You kind of see that we kind of very simple. We just construct our query string using f strings in Python in our Databricks notebook. We can then just take that query as is and create a view of the unpivoted data, and then run that as a Spark SQL command. So the performance comparison here is like trying to insert 1.25 million records would take 15,000 seconds or possibly more, and in the end, like this probably isn't even very usable because like in this database, trying to query that many records and aggregate them might even be just not like worth doing. Meanwhile, if we do it this way, because the rows are actually only 13,000, it only takes 2 minutes to insert them, and then it only takes like less than like 7 seconds to query this data in Spark or Databricks, or Databricks. So this view can then feed into additional pipelines that the lab or data scientists want to see. So we could actually like process this within a reasonable time frame. The user just uploads a file, kind of goes through this pipeline, and then it's already in a format that's best used for like aggregation in a pipeline where we're maybe doing some averaging or aggregation of this data across multiple experiments. So just to summarize what I just talked about, so laboratory information management systems face challenges when like processing instrument files from their varied formats and sizes. You kind of get just weird stuff from the instrument companies. Again, they're not software companies. One key thing is that use the packages to the best of your ability. Like, don't like try to fight pandas. Like, use its internal functions to help process data. And you can actually make some pretty simple code that does pretty powerful things. Finally, even like processing records at even a modestly big scale can actually be greatly simplified using PySpark in a way that like sort of our ELN software doesn't really work well because it's a transactional row-oriented database, not a place for aggregating millions of records. So this kind of like using the combination of these two creates a more effective like sort of solution for a lot of our scientists. So that I'd just like to acknowledge sort of the people that helped to make this work possible, like the data services software engineering team. I'm just the annoying product owner. It's like, hey guys, I got this great prototype. It should be really easy. And then Nope. The early fermentation team, who's like sort of the customer of this, they're providing a lot of valuable feedback for how this all works, and then you all for just listening in on this talk today.
So there's 5 minutes for Q&A. Who wants to go first? 10 minutes.
No.
Hey, thanks for the talk.
Yeah.
So you mentioned that you take the time series data and copy that into the data lake or warehouse.
Yeah.
What is that, like writing rows from the time series into the warehouse, or is it like a single like blob storage?
It's like, I think taking like, there's like sort of, we do like a batch loading process where like every like half an hour it just takes whatever's in the database, like goes through each of the tables that are there and just like copies any updates into there. So it ends up being so that like it's append only, where it kind of ends up like, I kind of brushed over a lot of the details, but like basically just copies as is everything over without really modifying it. So that's kind of how we get the data there, and then from there we do like, it's like subsequent queries to sort of clean up that data.
Okay, so there's no like transformation or like
No.
mapping row names or anything like, or column names or anything like that.
Yeah, we just like try to, as much as possible without doing many data transformations, just stage the data as is without doing anything to it. Just following like an ELT instead of ETL pattern. With that other data source, you can't necessarily do that because the columns change so much, so we actually have to pivot it first before it ends up in the database, because otherwise it doesn't make sense to have like columns constantly change. If it's like 0.01 this time and 0.02 next time, that's not really gonna work, so.
Thank you.
Anybody else? I think we have a lot more time.
Yeah,
So.
you could ask me about anything else.
Do you have a in-house built LIMS system, or is it a third-party like or vendor?
Okay, yeah, so the in-house LIMS system we essentially use, I kind of alluded to there, would be Benchling, which is just a software solution product. You're probably familiar with it if you're at all involved in biotech. We do have an in-house LIMS. Let's not talk about it. It's a disaster. All I have to say is don't ever rely on a series of contractors that constantly changing out every 6 months to work on an important internal system, because no one will know what's happening 3 years later. Chris, you have a question?
Yeah, Aaron, thank you so much for the talk. Could you share just a little bit more on the instrumentation, the different formats, and sort of like the scale and how you managed all that? Like, was it sort of this bespoke, I've got to figure out each feed by myself, and how do you keep track of that with a team?
Yeah.
You know what I mean? Because there's so many kind of different pieces, and I imagine people are using different equipment over time. So how does all that work?
Yeah, that is sort of one of the big challenges there, is because like each instrument company thinks that they're gonna like make their own custom format. I kind of skipped over that, but that one CSV I even showed that even had the nice rows, they have their own like custom format. It's like .oka, and I kind of like was trying to work with the fermentation side to be like, is there some way they could just like pull this out without having to like, because they actually have to load the file into the software and export it. And the software interfaces some of these instruments have are like straight out of the 1990s. Like they're just awful. But like a lot of it's all the way you can really interact with some of the things, like is that way.
Just to follow up, is that stuff generally kind of delimited text-oriented stuff, or is it binary, or
Yes.
both? Yes. Okay.
If you're lucky, it'll be like a CSV. And a lot of times it just is. I'm probably crapping on instrument companies too much, but like a lot of times it ends up being a weird binary formats or like other things. And like I know like it's very interesting how much you just get weird stuff all the time. And then it's like, and then so a lot of this is just like batch processing and stuff like that. Like when I say like people just like put like the CSV on their like thumb drive and then upload it somewhere else. It's not very fancy.
Hi, nice talk.
Yeah, thank you.
Similar question. Thinking a little bit about some of the practical challenges that you face day to day, do you encounter systemic errors in your instruments that the pipeline or data services team is responsible for fixing? And if so, where does that fixing happen? Does that happen upon ingestion in Benchling, or is that something that's happening in your data warehouse?
Yeah, so if there's sort of issues with like if I understand your question correctly, if there's sort of issues with data quality or other things like that, That's sort of where like our data operations or data engineering teams and like sort of data science downstream kind of come in. We just kind of take the data and when you come up with this situation, just join it together, and it's kind of like if you follow like the bronze, silver, gold kind of like thing for like how you like stage data. Like there's like a silver table that's like this is just this joined data together. Someone then kind of runs like a quality check pipeline to see if there's sort of issues with the data itself. That's sort of downstream from my team, but like that's kind of like where like some of that comes into play, where they're trying to find systematic issues and stuff like that. Because you know, no one ever accidentally uploads the wrong thing or associates the wrong data. It never happens. Nope.
Anybody else? We can take a long break, or can ask more questions. Yeah.
So it seems like a lot of time that we are using PySpark to solve like a complicated query issue that like a SQL cannot solve. But like SQL already built on top of like a nice infrastructure that like you can. So what happens if like I have something that's like I have to do it in a company server, but SQL cannot solve the issue, and I want to use PySpark to do it.
Oh yeah, you could. I mean, the way I kind of breezed over it a little bit, but like the way that we're calling like SQL is with like PySpark. So if you want to use the way that this is set up, since we're using Databricks, you can just like Databricks essentially has PySpark notebooks, and you can just do any kind of like PySpark things instead of SQL if you wanted to. There's nothing. This is a really simple case, like you can put in a presentation, but I mean, no, we can use PySpark to do more complex things that SQL can't. So there's nothing stopping us from doing that, if I understand your question correctly.
So what happens if something that like I almost have to pull the entire table out of Redshift and then just like move it into the server, and then from using PySpark to process from that point on, would that be like just, are there like any better alternative for this kind of problem, or?
I mean, in this case, we're not necessarily pulling the data as is from like our staging tables. We're actually creating views. So like the data only really gets, like it's not stored again. It's like getting processed when you access it. So it's not necessarily loading everything all over again. It's kind of like, as you access a view, it's kind of like stacking the queries together. Does that make sense?
Yeah, it's.
Maybe I'm not understanding what you're asking. That might be it.
Yeah, because for my problem is a little bit more specific, because like all our data is stored in the Redshift.
Yeah.
But then if I need to do the complicated processing, I have to do it in a server. So it's outside the AWS ecosystem. So that's like what I worry about, that like if I use PySpark, what I ended up basically have to just move everything from Redshift into another system, and then use PySpark to process it from there.
Okay, I see what you're saying. So in our case, we're not necessarily using Redshift to load the data. Like it's actually using Databricks' like native like Delta tables. So like we can just access them right there in the notebook. So there's no copying of data back and forth. And in general, if you're using Spark, you don't want to load up all the records in, right? That's kind of the idea, is that you kind of want to like delay actually loading data into the last moment, because you don't want to like load in like a terabyte of information or something like that, right? So is that sort of what you're getting at, or?
Yeah, that's the problem that I try to avoid
Yeah.
getting. So yeah, I think thanks.
All right.
Our next speaker is at 4:15. So we've got 2 more minutes if anyone has the last question.